On today's episode of the Ag Irrigation Collective, we're going to visit about VFDs. Stick around. Hi, I'm Wes Schaefer, your host with the Ag Irrigation Collective. Sure appreciate you stopping by today. We're going to take a look at a question from Reddit again. We've got Sneaky Cat 7312 asked the question, what is a VFD and do I need one on my farm? Well, Sneaky Cat, we're going to take a look right now, and I'm actually going to use a supporting document by LSU that they put out that basically goes into and talks about what VFDs are, and I'll let you determine if you need a VFD on your operation or not. And so we're going to go through what a VFD is and how they can be useful within irrigation on your farming practices. So what is a variable frequency drive, or VFD? And it is basically an electronic drive system used to control electric motors. Its purpose is to vary motor speed by controlling input frequency and voltage. So a variable frequency drive converts AC voltage to DC current and can be thought of as pulsing this DC current to the motor to vary the motor speed. VFDs are energy-saving devices and load management devices that belong to a group of different devices, sometimes known as adjustable speed drives. VFDs save energy by varying this speed and input energy required for the corresponding load. VFDs are an alternative to soft starts. So basically there's three types of motor control panels that are common. There are probably several others, but there are three common types. The first being an across-the-line panel, and a second being a soft start, which I just referenced, and then the third being this variable frequency drive, also more commonly referred to as a VFD. Not only within irrigation, but VFDs are utilized anywhere there's an electric motor. A lot of HVAC stuff utilizes VFDs. A lot of industrial stuff that uses electric motors utilize a variable frequency drive in an effort to control that motor speed depending upon the load. There's a lot of fans that are run on VFDs to control the speed of a fan. Essentially, it controls the speed of the motor, thereby controlling the speed of the fan. So anyway, long and the short of it, VFDs are basically the third tier in from cross-the-line panel, soft start, and then you get to VFD. And VFDs are useful when slower motor speeds can provide those energy savings. And so when a VFD is used to start a motor, the motor starts slowly before coming up to full speed. A VFD can be thought of as putting a throttle on your electric motor, as if you were to throttle up a diesel motor or a gas motor. This way you get to control that speed of that electric motor. That isn't standard when you just buy that motor. There is a motor control that's necessary. In this case, is a VFD. So how come would you want to use a VFD in irrigation? Well, we'll go through a few bullet points here. Variable frequency drives provide for a gradual increase in speed of motor at full load. The full load motor torque is available even at slow speeds. So from a power utilities perspective, this long time for startup, it reduces the startup load. And for initial line loading, that is often several times the full motor load. So if you can ramp up slowly instead of all of a sudden hit with an across-the-line panel, that certainly helps with brownout scenarios with some of these utility companies. Across-the-line motors, the utility must be able to accommodate the inrush of voltage drop necessary for that motor startup. And a VFD reduces that inrush current by spreading the voltage drop across a longer period of time, basically. And within VFDs, you can program those to have a ramp-up time that is slower or longer, depending on what you're doing. several VFDs, and the wording could be different. The terminology within the user interface may be different, but there are some, and Danfoss is one that I'm thinking, that has what's called a pipe fill function. And within the pipe fill, that goes really slow. And if you've got, let's call it, a mile of pipe to fill, before you ramp up to full speed, it'll slowly ramp that up, keeping that at a constant. It may get up to, say, 45 hertz while it's doing a pipe fill mode, and you get to set that time frame within your user interface of the VFD. So VFDs may overcome the 10 to 15 horsepower motor limitation for single-phase service. Because a VFD converts AC to DC for the motor, the phase of the input source does not matter. This allows for larger motors to be used where only single-phase service is available. So essentially saying you can convert single-phase to three-phase utilizing a VFD, and we do that very frequently within irrigation. However, your transformers must be sized to provide the required current, but where there is a high three-phase service installation cost, VFDs can be more cost-effective. And a lot of cases, your line may only be a single-phase line, and not only do we consider high three-phase service installation cost, there may be the scenario that three-phase is not even in the realm of possibility because the utility won't bring three-phase to you because it would require a complete line upgrade or something of that nature. So variable frequency drives allow for constant pressure as well as automation. The VFD can accept instructions from a programmable logic controller, which we call them a PLC. And the PLC is an industrial controller that provides the ability to accept inputs from sensors and outputs to control motors. For example, in irrigation systems, a pressure sensor can be used to report pressures to the drive to maintain constant system pressure. This is especially useful in center pivots and micro irrigation, as well as wheel lines, where flow rates may vary, but constant pressure is desired. For example, on a center pivot, when you turn on an end gun, but you don't run it all the time, on your corner swing arm systems, where when it's tucked in, you may shut off that entire 305-foot section, and also some variable rate irrigation within your pivot that may alter that flow. This gives your pump motor an opportunity to ramp up or down to maintain what demand your pivot is requesting. And so a VFD can maintain that constant pressure through varying the motor speed, thereby controlling the flow when these components are cycled. Also, VFDs can reduce the thermal and mechanical stress on your pump motor and reduce water hammer in your irrigation system. The slow start compared to the rapid start of an across-the-line panel reduces wear on motors, pumps, and irrigation systems, which include your pipe. With older irrigation systems, the reduction of water hammer, this is your pipe we're talking here, can extend the life and reduce the potential for leaks and failures. There's a lot of times when we may put on a new pump and it just has an across-the-line panel on an existing system. Let's say that they were running wheel lines or something, and we're just upgrading a pump, and we go and crank that Hummer up, and I'll be darned if we don't blow a line out down at the bottom because we ended up with some water hammer or something crazy like that. So VFDs are helpful for that. And soft starters also are helpful for that, but there's some additional protections and features of a VFD that can be beneficial for you. So we're going to get a little bit scientific here because I'm going to go into how a variable frequency drive works. And this may get a little deep for some, including me, but we're going to dive into it because it's interesting for everybody to start to learn about. So the rotation speed of an induction motor is fixed and determined by the frequency of the supply voltage. Alternating the current supplied to the stator windings of the motor produces a magnetic field that rotates. Within the winding of the motor are pairs of magnetic poles Dividing 60 hertz by the number of magnetic pole pairs in the motor will give the revolutions per second, thereby also giving the revolutions per minute of the motor. For example, an 8-pole motor has 4 pole pairs, and the magnetic field will rotate at 15 revolutions per second. This is equivalent to 900 revolutions per minute, and this is also assuming of an electrical signal of 60 hertz, where 60 hertz is divided by 4 equals the 15 revolutions per second. When the rotating magnetic field is induced, the rotor of the motor will accept to follow. The load on the motor, however, causes the rotor speed to slip slightly behind the rotating field speed. And that's one reason why you'll have maybe, say, an 1800 RPM motor that on the tag is stamped 1770 or 1740 or whatever they're stamped on there. They're just slightly below the actual rotating field speed. Induction motors rotate close to synchronous speed, though. The most effective and energy-efficient way to alter the speed of the motor is to change the frequency of the applied voltage, thereby our entire discussion of a variable frequency drive. Variable frequency drives change the fixed frequency supply voltage to a continuously variable frequency. This allows for adjustable motor speeds. The conversion is accomplished using a rectifier and inverter stages. In the rectifying stage, the rectifier converts three-phase to 60 hertz power from a given utility supply to direct current voltage. And their standard industrial motor voltages are 208 volts, 230 volts, 380 volts, 415 volts, 460 volts, and 575 volts. So there's also that to be mindful of when choosing a VFD is what voltage your motor is. There's some that are dual voltages. We have some available, and these are probably the most common that I deal with are the 230/460 volt motors. Voltage and motor speed is varied by altering the firing pattern of electronic switches or insulated gate power transistors. In the inverter stage, the insulated gate power transistors, sometimes referred to as power transistors, switch the rectified DC voltage on and off to produce an alternating current at the desired new frequency. A control system with an electronic circuit receives continuous feedback from the driven motor and adjusts the output voltage to frequency conversion. As electronics continue to advance, the AC, DC, AC conversion process of a VFD is likely to become more efficient, and currently efficiencies exceed 97.5% efficient. That's extremely efficient, by the way, at 97.5%. So I don't know, even with increasing efficiencies and with the advance in continued electronics and things like that, to get higher than 97.5% efficiency, that's pretty darn good. So now we're going to get into the application of VFDs and where you may use this. Applying VFDs to a centrifugal pump can result in significant energy reduction. Motor-driven equipment often is operated at reduced loads or restrict flows, and the opportunity to decrease energy consumption becomes much greater compared to equipment operating at maximum throttle or flow. Centrifugal pumps consume energy proportionate to the cube of the flow rate, and a small reduction in speed or flow can lead to a great reduction in energy consumption. When lower flow rates are required, decreasing the speed can lead to large energy savings. The VFD and motor, though, must be compatible, and typically, existing motors in good condition can be used with a VFD. Motor windings are the primary concern, since the VFD will cause more electrical distortion than an across-the-line application. There is an insulation test that can be conducted. It's called a Megger test, and it can determine the resistance between motor windings and ground. A resistance of 300,000 ohms or greater is acceptable. So this test should be performed just after the motor has been operated because dust and moisture can affect the test results. So by running that motor and operating that motor, you can blow the dust out and dry that moisture up. Do not perform an insulation test with a VFD connected to the test unit because the high voltage used in an insulation test or a Megger test can damage your VFD. In some cases, a motor should be rebuilt before being put into service with a VFD in the event that your insulation is not adequate in order for that Megger and for your VFD to function properly and without damaging your motor. High or premium efficiency induction style cast iron motors are preferable to lower efficiency motors because the windings and components. Slowing a motor does create additional heat that the fan motor or the fan on the motor may not be able to dissipate as well as it would at full speed. So keep in mind that electric motors are and have been typically designed with a fan on them and built into the case of them, and those are designed to run at the full 60 hertz of speed. And if you're upgrading a pumping plant or considering rewinding a motor, visit with your VFD provider about your compatibility before you get too deep down in the road of throwing a VFD on before you actually know if your pump motor is compatible with it. So some considerations for variable frequency drives. You want to consult your utility provider about any discounts or credits that can be given for installing a VFD as a load management device. In our area here, there are some credits available from the utility service, the electric utility, that I believe they receive a federal government grant for offering different incentives for putting VFDs on the system. The one thing that it does for the utility is it alleviates that initial startup. And we get into some big motors. Let's say you're on a 400 horsepower deep well motor, hollow shaft, pulling, let's call it 400 feet, and you run that on an across the line panel. That power company is going to notice the power usage on the spike of the uptake the minute you fire up that motor. So a VFD is very helpful and handy, and some power utilities require a VFD depending on the motor horsepower, that if you get in such large horsepower, they say you have to have a VFD under these situations. And also you want to visit with your utility to learn if there's any known issues with VFDs in the service area. They can cause some frequency related issues. There are cases where we've seen VFDs be installed and then the antennas on a buried wire pivot corner have needed to be changed from one frequency to another for those antennas that are reading the wire in the ground. And it also can be a concern that would limit the effectiveness or require filters. And the filters here that we're referring to are power filters or line filters within your VFD installation. In most cases, a VFD will be a welcome solution by your utility to reduce the effects of startup motor loads on the utility grid. So, of course, you want to find a reputable dealer and service provider who are knowledgeable about VFDs for your irrigation application. Most irrigation dealers deal in pumps and VFDs pretty readily, but it's good to vet those out to make sure that you're getting somebody that is knowledgeable within VFDs. Service providers are not always associated with irrigation companies, although some irrigation manufacturers now offer VFDs as original equipment. For example, center pivot manufacturers, I believe the big three, which would be Valley, Zimatic, and Ranke, all provide VFDs as original equipment. Please correct me if I'm wrong in the comments, but I believe that's the scenario. I know it is from Valley anyway, being a Valley dealer myself. A VFD for irrigation, though, should have a manual and automatic on and off modes. The manual mode is used to test the motor and drive for operation without any automation or sensor input. So this is in the event you're working on it, you can actually run it without having to have water pressure present. There should be an emergency kill switch or lockout somewhere on the panel that stops all movement or shuts down all power. That's a good safety feature, as well as other purposes beyond safety, is just to be able to shut the darn thing off. And you also want your motor speed to be altered manually. Typically, there's a rheostat or a dial type of a control. Also, just a dial on the front of that panel. And also, it's advisable to control the VFD using what's called, we discussed it a little bit earlier, a programmable logic controller, or PLC. And I've not seen any VFD without a PLC. So it's not only advisable to control your VFD that way, that is how VFDs are run anymore. If a centrifugal pump surges or has lost prime, or a part has broken on that pump, the system should be able to shut down without causing further damage. Centrifugal pumps that run dry can boil the water in the volute, so incorporating this safety feature into a VFD is an added safety option. A high pressure and low pressure shutoff should be incorporated also into the logic of the PLC or your VFD control system. If a pump cavitates, some VFDs can sense changes or irregularities in motor loading. So a lot of these VFDs will sense different watts being used, different amps being used, and they will, and this is all based on how you or the manufacturer of the VFD programs that PLC to say, okay, with under this certain amp range, we don't have any water movement. So we need to shut down because we have a dry well scenario, we have a dry pond scenario, whatever that water source is coming in, then that VFD can shut it down, and that is one of the safety features of a VFD that's pretty handy to have. And of course, to be able to shut that down with your PLC without you present can eliminate pump damage. And depending on your application, these safety features could offset the cost of the VFD by avoiding potential pump repairs or complete replacement of pump motors. VFDs involve electronic equipment that generates significant amount of heat during the operation, though. VFDs should be mounted in a NEMA 3R enclosure with ventilation, and in most irrigation applications, those are exactly what we see, and those cabinets have been used in agricultural settings and operate well as long as, and these filters here are properly maintained and cleaned. And those filters that I'm referring to are air filters. And it basically, at the bottom corner of one cabinet, let's call it the bottom right, is an intake, and then the upper left is the exhaust, and you're just bringing air up and across basically that VFD and across the back of that VFD where there is some cooling fins to create some additional surface area for cooling. And if you're bringing that fresh air in, and naturally, if the filters within those intake and outlet areas are clogged, you will eliminate or very greatly slow down your airflow, causing excessive heat within your VFD, and that can certainly damage the VFD. As with any electrical installation in the agricultural environment, if you need to install proper safety shutoff and lightning protection, lightning arresters and surge protection are designed to protect against stray voltage and current from direct or nearby lightning strikes. These devices, and they're typically disposable once they get hit with a lightning strike, they're designed to absorb or limit the voltage spike before it passes through the motor and other electronics within the panel. So the surge protector, there's some called a strike zorb, and I think a strike zorb, I don't remember the brand that we utilize, but they are designed to take up to 1,000 lightning strikes before they are ineffective. So they are actually not as disposable as like a surge protector that we may commonly see. There are also some cost savings of VFDs, and this example is not today's prices, but I'll give the example to give a little bit of an illustration here. So on a 40 horsepower motor, if it's operated below its maximum capacity for about 40% of the pumping season, a VFD could save as much as $6,000 during 6 months of operation in that year. If the estimated cost for the VFD in this example is about $5,000 and another $3,000 to $4,000 is required to install the VFD, the payback time would be less than 2 years in this example. So there are some cost and payback for VFDs, and where there is some safety benefits, there's some power company potential benefits there. So we sure appreciate this question coming in from Reddit. I will allow you and all of our listeners and viewers to draw your own conclusions if a VFD is right for you on your operation. Typically, the answer is yes, absolutely. However, the initial cost to install a VFD is not cheap. However, it may pay for itself over time, as we discussed very recently here, but it's all depending upon what your goals are within your irrigation management style and how you choose to operate within your farm and your farming operations. And so take this for what it's worth. I appreciate you guys visiting with us a little bit today about VFDs. I do have intentions here in the future to get a VFD expert on with us that we can dive into this even a little deeper to talk about VFDs and where we've seen them be real useful. But anyway, that's going to wrap up the podcast today. Appreciate you guys being with us and hanging out with us today. Be profitable, my friends. We'll catch you on down the road.